Hi, everybody, and welcome to Lecture 4. In this lecture, in the two parts, I will be talking about the modern climate of Antarctica, summarizing and following up from the discussion last lecture about the overall climate of the Earth as well as atmospheric circulation. The second half of this lecture will start with a specific form of deep ocean circulation and then conclude the climate part of this class with a brief discussion of some of the articles that I had you read, as well as an introduction to climate research, and that will bridge us into the upcoming unit on geology and the history and the geologic and paleontologic history of Antarctica, basically what the rocks and fossils tell us. And what in particular the rocks and fossils tell us about how we got here, how we got to Antarctica being this cold place. In the last lecture, I talked about solar radiation, the greenhouse effect, and the structure of Earth's atmosphere, emphasizing the ozone layer in particular and the Antarctic ozone hole. We're going to head from that today into a discussion of the modern climate of Antarctica, and then a talk about ocean circulation and the role that ocean surface circulation plays in regulating Antarctica's climate. Now, I do have a couple quick announcements about this week. I first want to say thank you for being patient with some errors that we had to fix with lab number 1, and check any emails you've gotten from your TAs just to be sure that you've fixed anything that's necessary. If you have not yet started the lab, I highly recommend you do so very soon, and make sure that you check the TA presentation and any of the files in the files needed before you attempt to take the lab quiz itself. There are going to be TA virtual office hours throughout the rest of the week, so come to those if you have any issues. Speaking of some other assignments, I did want to mention before that I can help you with the labs, but remember that the TAs are your first people to go to with the labs. They're the ones in charge of the laboratory sections, and they're there to answer questions about that. I can help a little bit, but questions about everything else go to me, like the quizzes, the reading assignments, and the lectures, but the labs are, for the most part, the TAs' domain. Now, the reading assignment is not due until February 14th, but I just wanted to remind y'all that it's due then in case you want to get a head start. This is the news article write-up. Very importantly, I will not be posting a lecture this coming Monday. Next week is going to be a little bit different overall because Monday is Martin Luther King Day, and the school observes that as it's a federal holiday. UCSB observes that. So I will not be posting a lecture, and I will not have a discussion session that day. Normally, I do review on Mondays. I will instead be doing a review that Wednesday, January 20th, during the discussion session that day. And that might be of interest to you because there is the first quiz coming up. The first quiz I'm actually going to open it on Monday, but it will not be due until the 24th, and it's possible that you may not want to take a stab at it until you've attended or seen the video from or gone to the review session. I said gone to twice. You know what I mean. But there'll be a review session on January 20th if you want to go to that before attempting the quiz. The quiz is going to cover lectures 2, 3, and 4, aka today's lecture, the lecture I posted Monday, and then one of last week's lectures. Lecture 1 is not going to ever be on the test. And it also covers, the quiz will also have a few questions related to the articles and the video I had you watch this week. Regarding extra credit, there is actually another opportunity tomorrow on Thursday, January 14th, and the Zoom link is here. For those of you who want to join, there is another colloquium about landslides in California, which should be pretty cool, happening tomorrow. Unfortunately, the radio show that I had previously mentioned as a possibility for extra credit is not airing anytime soon again. I will see if I can think of another system for doing Write About Science media, and I will keep you updated with that. But for those of you who were interested in listening to the radio show, that is sadly not an option. So, let's talk about the modern climate of Antarctica. It's cold, it's dry, it's windy. Why is it cold? Well, remember last lecture we've talked about the fact that because it's at a polar latitude, it is at such an extreme distance from the equator that the sunlight is spread out and not as direct because you're at the curve, because it's much more curved at the poles. And then you also have seasonal coldness. You have the polar winter where it's completely dark from the tilt of the Earth's axis. A factor that we're going to talk about more today is what the Antarctic Circumpolar Current does, and in general, the fact that Antarctica ends up being isolated from movement of warmer water elsewhere in the world. Because warm water brings heat to the continent, if that's not reaching Antarctica, the continent of Antarctica is going to be cold. What's a good counterexample to that? think of the Gulf Stream in the east coast of the United States. Now, another thing we'll talk about today is albedo. Albedo is a consequence of all the ice, and it's interestingly kind of a cyclical running consequence of the ice, because you get ice from it being cold, and then it turns out the presence of ice makes it even more cold. Ice reflects sunlight, and less sunlight hitting, more sunlight being reflected out means that Antarctica absorbs less heat. So the ice actually keeps Antarctica colder. Now, why is Antarctica so dry and windy? Antarctica, whether or not there are ice caps in Antarctica, it's going to be a high pressure zone. It is where air that rose around 60 degrees south and dropped its moisture there falls very close to the South Pole. It falls as a very cold, dry mass of air. Now, something that happens in Antarctica in particular is that since there is the big dome of ice covering most of it, and especially in East Antarctica, that slopes downward towards the coasts, that accelerates the winds. You get these really strong winds called katabatic winds, or pressure winds, going out from the center. And the presence of the ice makes that wind so strong, because the ice is funneling the winds to the edge of the continent. And also, a consequence of the Antarctic Circumpolar Current is that the winds in the Southern Ocean can just go in an unbroken circle around the continent and form this high-speed vortex. Antarctica has not always been like this. We will talk a little bit at the end of this lecture how even though when Antarctica has for a long time been pretty close to the South Pole, but it hasn't always been quite as isolated. And we'll talk about how those two counterbalancing things have either made Antarctica kind of habitable or not so habitable over the course of geologic history. But that's more for next week's topics. Going specifically into albedo. Albedo is a concept you might have come across in discussions of global warming. And albedo has the same Latin root as albinism. Alba means white. If something has high albedo, we're talking about a surface, a substance, say ice. If something has high albedo, it's going to reflect a very high percentage of the sunlight or the general radiation that's hitting it. Something with high albedo is like a mirror. It reflects back more of the radiation and also a wide variety. You hear that white reflects light. Well, yeah, white ice caps are going to reflect they're going to reflect all wavelengths of visible light back, and also a lot of UV radiation back. So another example of something with high albedo is actually deserts. Deserts are pretty light. If you have sandy deserts, those sands are made of quartz. That sand is pretty light colored and actually reflects a lot of the light back. Something with low albedo is going to be something that's dark. So most of the Earth's surface is going to be covered in pretty dark soil, or there's going to be vegetation, grasses or forests covering it. Forest in particular has very low albedo. Darker colored substances are going to absorb a lot more wavelengths of light. Something that's black absorbs all light. And this is true of the ocean also. The ocean is a dark blue and the ocean looks like a dark blue and is going to absorb a lot more light than frozen water, than ice is. And that's something actually to consider with global warming, and global warming not just in Antarctica, but in the Arctic also, because the Arctic, you have sea ice covering the ocean, but if that sea ice starts to melt and more of it is replaced with liquid water, the ocean water is going to absorb a lot more of that incoming solar radiation than the ice did, and it's going to get warmer. So losing ice caps actually contributes to global warming in that way. But if you have ice, the presence of the ice is making things colder. And Antarctica has a much higher albedo than the rest of the Earth. Because over 99% of the continent is covered in ice, Antarctica reflects 80% of the incoming solar radiation. And that makes for a very cold continent. It also helps keep the Earth cold as a whole. And we'll talk about how the presence of the polar ice caps, when they first formed at all, that brought the Earth towards its current ice age. This is one example of what you might hear of referred to as a positive feedback loop. And we will come back to the idea of positive feedback versus negative feedback. but I want to mention that the term positive has absolutely nothing to do with whether something is beneficial or not. What positive feedback means is that something happens as a result of something else, like, say, temperatures drop, so you start forming an ice cap. An ice cap starts to cover up previously barren ground that was covered in vegetation. The ice has higher albedo than the vegetation. The ice shines more radiation back, and the area around Antarctica gets colder, and more ice starts to form as it gets colder. More ice means that even more albedo, the continent has even higher albedo, even more radiation gets reflected out, until eventually the entire continent is covered in ice and its surrounding ice shelves and sea ice. That is essentially what happened to Antarctica, and how the polar ice caps first formed. Now, before I do anything else, let's go back to a quick review of the Coriolis effect, just because it's a concept that comes up quite a bit, and it's extremely important. The Coriolis force is an inertial force, which means that what's happening is that an object is keeping its original speed, in a sense. If we're on the Earth, we are rotating with the Earth at whatever point we're at. If you look at this diagram in the middle, this shows that the equator is actually rotating a lot faster than the poles, or even, say, 30 or 60 degrees north. This is because you'll notice the Earth is much more bulged out at the equator, and it's rotating like a top would. It's rotating fastest at its widest spot, so that points along a single line of longitude. You'll see that if you go from the North Pole and simply go straight down, you are tracing a single line of longitude all the way down to the South Pole. Any point that is along that line, you're going to experience a new day at the same time. Earth rotates, and someone standing on this line of longitude near the North Pole will come to a new day as the Earth rotates at the same time as someone standing on the equator. It has to rotate faster at the equator. So this causes the Coriolis effect. This means that if you're closer to the equator, you are rotating faster than somebody who is standing closer to the pole. The Coriolis effect doesn't really have much of an effect if we're just walking, or if we have cars moving at a pretty low distance, by the way. It is most relevant to either masses of air or water. Air in particular, the air moves the water, or to airplanes which are moving fast enough, or projectiles. But the Coriolis effect is something that airplane pilots have to keep into consideration. If an air mass or an airplane is in the southern hemisphere heading from the equator towards the South Pole, the Earth moves from left to right, from west to east. That airplane, when it takes off, it's going to kind of act like it's still moving along with the rotation of whatever objects were also at the equator. Like, the airplane was on the ground and it was rotating with the rest of the Earth. It was rotating the rate of the equator when it was on the ground. And then when the airplane leaves the ground and heads south towards the South Pole, it actually conserves that original spinning velocity it had at the equator. What's happening is that it's going to end up overcompensating. If you don't do anything, the airplane is going to be intending to head south, but it's actually going to end up being deflected to. If you look at this diagram on the right, the lower right arrow shows what happens with air masses and projectiles heading away from the equator towards the South Pole. They get deflected in the direction of Earth's rotation. They get deflected to the east. Now, if you'll notice, if you were to trace a line from the equator to the South Pole, that would be one line. This is to the left of that original direction. And that is what I mean when I say that in the southern hemisphere, objects get deflected to the left, and in the northern hemisphere, objects get deflected to the right. It is to the left of the quote-unquote intended path, aka the path that would occur if Earth were simply not spinning. And the difference in the hemispheres is because Earth is rotating the same way no matter what, but you're fastest at the equator and slowest at either the North Pole or the South Pole, meaning that the deflection is basically being dragged. It's being dragged by Earth's rotation, essentially. It's being deflected in the direction. You're you're being deflected in Earth's rotation. A counter example, actually, of sorts, is that not exactly a counter example, but if you're in the reverse situation of starting at the South Pole and going towards the equator, you're going to end up off course because you are moving more. You kind of think that you're rotating more slowly than the Earth you're passing over. You're rotating fastest at the you would be rotating fastest at the equator. An object launched from the South Pole is going to kind of lag behind in a sense. It's going to, instead of traveling this way, it's going to kind of get dragged over here because it actually has a slower spinning velocity than the ground underneath it. As you go closer and closer to the equator, it's spinning faster and faster and faster. But if you are the airplane going from the South Pole, you're not really registering that. You are still kind of spinning west to east at the same rate that you were when you started. And so you end up, in a sense, behind where you would be if you were on the ground. Again, I am very happy to discuss the Coriolis effect in office hours because it is something that I also took time to understand intuitively, and I'm happy to go over it multiple times. The Coriolis effect messes with air. The Coriolis effect causes air masses of Earth, air masses that are moving around Earth, to not travel in straight lines from one latitude to the other, but to kind of be curved. And if you look closely at the arrows, it looks like they're approaching the lines of latitude without ever really reaching them. In math, that would be referred to as asymptotically. And that is what happens, actually. If one has come across the concept of the doldrums, aka the equator having essentially no wind, that's because the air moving from 30 degrees north or south and traveling along the surface of the Earth to the equator, the Coriolis effect deflects that air ever so slightly away. It never quite reaches the equator because it's deflected by the Coriolis effect. It rises before it actually reaches the equator itself, meaning that right along the equator itself is this dead zone where there is no wind, because the wind is being funneled right on either side of it and then rises up there, but it doesn't quite reach the equator because the Coriolis effect sends it in the wrong direction. Now, I do want to go back to the fact that you have high versus low pressure zones. Remember that from our last lecture that if you have a place where air is rising, that's going to cause low pressure. If you have a place where air is falling, that's going to cause high pressure. The poles are zones of high pressure. The poles are where relatively warm air with a lot of moisture rises at 60 degrees north and south. That air rises up in the atmosphere, gets too cold to retain much more of its water, and that water drops out at 60 degrees north and 60 degrees south. The air travels in the upper atmosphere until it becomes cold enough to sink at the poles, and the falling dry air produces a high pressure zone. And this is something that has been consistent throughout Earth's history. The poles have always been high pressure zones, and this was true even during the dinosaur age when the Earth was warmer as a whole, and as a consequence, Antarctica was warmer. And also when there was no Antarctic circumpolar current to isolate the continent as strongly. Now, what does the high pressure mean for the windiness of Antarctica? So Antarctica's South Pole is home to an anticyclone, a rotating mass of descending dry air. It's a high pressure zone. That air is very cold as well, and it's colder than the air you would get at 30 degrees because the polar sun doesn't heat Antarctica's air very effectively, and the infrared radiation coming from Earth isn't really a factor. You have the ice cap. So remember that the ice caps themselves are kind of like these domes. They're sloped with the highest point in the interior of the continent, and then they slope outward because you basically have ice flowing from the interior outward, at least in East Antarctica. It's a little more complicated in West Antarctica, but East Antarctica actually makes up most of the continent. So Antarctica is overall a big ice dome. What does that mean? Well, you have air falling at the center. That air begins to make its way down the ice dome, and as it goes downhill, it accelerates. It goes faster and faster and faster. So this is called a katabatic wind, a pressure wind, also known as a draining wind. And These winds produce a constant blow of intense wind from the interior of the continent outward. This is a huge reason why Antarctica just feels like there's wind constantly blowing, because there is. It is that high pressure air making its way out from the center of the continent, and it would not be moving as fast as it was if the ice dome was not accelerating it. So think about what that would mean in periods when Antarctica was still close to the South Pole but didn't have an ice dome. Yes, you'd still have high pressure and not a lot of precipitation, but not necessarily quite as strong a wind. And when the winds get closer to the edge of the continent, they can become channeled into the few exposed valleys, because remember, there's just going to be more exposed rock near the edge of the continent, because the closer you are to the ocean, the warmer it is. These katabatic winds can become channeled into these narrow valleys and become even stronger wind tunnels. So the dry valleys exist as they do because katabatic winds that are already moving fast get channeled into these valleys, and they begin to blow away any snow that has built up, and they stop any further snow from building up. These valleys are extremely windy. They're windier than the interior of the continent even, and it's honestly, dealing with the wind chill was not easy when I was there. Something else we'll talk about that these winds do is they continue to blow out to the edge of the ocean, and they literally blow the sea ice away, which will have important consequences for ocean circulation. So we're going to make a jump from air circulation into ocean circulation. And we start with air circulation actually before, because it turns out that one of the two primary types of movement of ocean water is mostly driven by air. There are two ways in which the water in the ocean moves. Either water at the surface is moved around by a combination of winds and the Coriolis effect, and the Coriolis effect determines which direction the currents go in, which we will talk about next. Water also circulates from the top of the ocean to the bottom through the different layers of what you would call the water column. And that is actually much, much slower over the course of years or hundreds of years or even thousands of years, as opposed to the much more rapid wind-driven surface movement. Deep water movement is largely not driven by wind, because naturally the wind doesn't really have much of a factor deep below. Wind plays a role in the facilitation of the water sinking, as we'll talk about, but it's driven by differences in density. Not all water is going to be the same density, because water changes density at different temperatures, and how salty the ocean water also varies. And water moves throughout the ocean due to variance in salinity and temperature. Remember that if you have, really in science, if you have a difference, like if you have more heat in one area and less heat in the other, heat will flow from where there is more heat to less heat. The same way that the katabatic winds are essentially flowing from high pressure to low pressure zones. And in general, the different layers of the ocean do not mix very well. The surface ocean does not mix well with the deep ocean, because substances of extremely different density do not mix well. Even if it's chemically more or less the same thing, even if it's just seawater. But if they have rapidly different amounts of salt, they will not mix very well. The interesting thing is that some of the really important steps to this global process of ocean water circulating around, much of it is initiated by the specific conditions in Antarctica. So we're first going to talk about surface circulation, and we unfortunately need to talk about the Coriolis effect almost before we do anything. So something that I want to establish right away is that when I talk about the direction the wind is going in on this slide, we have already taken the Coriolis effect into account with the wind. We don't need to look at this wind arrow and second guess ourselves and think, oh, the wind is going to get deflected this much. No, the wind has already been deflected. We have already dealt with that. We have already dealt with the fact that the wind has been moved from the direction that it would go in if Earth were not rotating. And that's what you need to remember. Earth rotates, and different latitudes don't rotate at the same amount, and that causes the Coriolis effect. So an interesting combination of the Coriolis effect and wind friction causes what is called Ekman transport. And Ekman transport is the movement of water at 90 degrees relative to the direction of the wind that drove the movement of the water in the first place. The wind is what is driving the water moving, and you would think that the water would just move in the same direction as the wind. That's not what happens. The water actually overall moves at about 90 degrees. Now, something I want to point out to this diagram is you'll notice there's a couple of different arrows. It shows a surface current being deflected about 45 degrees. And as you go down in the water column to the depth of about 100 meters, you get different arrows that are pointed at different angles, you'll notice, and they get smaller. The arrows being smaller indicates that the force is less intense. In physics, they'll illustrate the size of a force or the size of the intensity of movement by the size of an arrow. And just as with wind directions, you get a clockwise deflection from the wind in the northern hemisphere and a counterclockwise deflection from the wind direction in the southern hemisphere. So the term Ekman spiral refers to the fact that the layers of water are not all getting deflected the same amount. You have to kind of think of you want to think about layers of water molecules. Water is made of molecules, and on a microscopic level, on an atomic level, those water molecules are kind of bumping into each other. The water molecules at the top are going to move, and that's going to affect them. It's going to drag around the water molecules below them. That's going to affect the layer below them. It's kind of like if you have a deck of cards and you sort of smear the deck of cards across the table. The top one is kind of, if you're putting enough pressure on it, the top one is dragging the other ones with it, but they don't quite go in all the same direction. What happens is that the surface layer gets deflected by 45 degrees from the original wind direction. And that's the strongest. That's the most amount of water gets moved at the surface. The surface water drags the water underneath it. However, because of friction, not all of that energy is conserved. Some of the energy that could have gone to dragging the water underneath it gets wasted on friction. So you end up with the second layer of water below has been deflected even further. It's been deflected, this is the northern hemisphere, it has been deflected to the right of the surface current direction. You'll notice the arrow is smaller. That's because it's weaker. The water was disturbed to a lesser extent because a lot of the energy was wasted on friction. Even more energy will be wasted on friction with the layer below, where you will notice that the water has once again been deflected to the right of the direction of the layer above it, but it is weaker because friction has caused it to be wasted again. As you go down, you get smaller and smaller amounts of, you get water that is more and more deflected to the point where it spirals. At the deepest point that you get any Ekman transport, 100 meters, the water is almost going the opposite of the original wind direction. But to actually summarize what direction the overall current is moving in, because we're interested in the overall direction of water. And the top 100 meters is often kind of what we're interested in terms of how is the surface water moving. Mathematically, you make a weighted average of this. You take an average based on both the directions of the different layers of water as well as how strong the movement is, and you end up with an overall direction that is 90 degrees to the right of the original wind direction. That would be 90 degrees to the left of the original wind direction if you were in the southern hemisphere. On this diagram, the little red arrow underwater shows where the water overall moves. And this might be confusing because you're thinking, wait, how can the water be all moving in different directions? We're taking, again, a weighted average, basically. The different layers of water all move in slightly different directions, but the overall flow will transport water 90 degrees, either right or left to the original direction the wind was flowing in. And once again, this vector showing the wind direction, we have already dealt with the Coriolis effect for it. The wind has once been disturbed by the Coriolis effect. When the wind causes water to move, and friction, I say friction is causing a waste, but friction is the reason that wind can drag water to begin with. If there were no friction, that would not happen. When the wind drags the water, it gets disturbed a second time by the Coriolis effect. And this is why studying currents is a lot more complicated than one might guess, because there's a lot of geometry you have to take into account. Now, something interesting about Ekman transport is that you get something called geostropic flow. You get low pressures and high pressures from the movement of water. And water gets piled up by Ekman transports in some places. Often, if you have wind currents, if you have one wind current going in one direction around a mass of water and another wind current going in the other direction on the other side of that mass of water, their combined movement will create it'll create kind of a perpetual motion circle that's very hard to escape. Because what'll happen inside of that gyre is that the water will be rotating it'll be trying to reach the center, but will never quite get there because of the Coriolis effect. And the water will be funneled into this gyre and will have a very hard time escaping. The water doesn't easily just sink down deep below because, as we'll talk about, surface water has such a different density from deep ocean water that the two do not easily mix. And oops, I apologize for that. One consequence of this in the North Pacific is that you have a gyre caused by this current north of the gyre and this other current south of it. You have the Coriolis effect creates water rotating towards the right in the northern hemisphere, and then this way in the southern hemisphere. And that, to a big extent, traps the water inside. The water can get out to some degree, but it's kind of much more calm in the middle. It's kind of like an eye of the hurricane type of situation. You have the water sort of being piled up into here, but it's sort of flowing around. And the wind patterns create this large area where water is being funneled into it, but doesn't escape easily. And whatever is being carried by the water gets trapped in there also. And that includes a lot of garbage, because the Pacific Ocean is going to have all of the trash coming from North America and Asia and Australia and South America. The Great Pacific Garbage Patch is actually two separate regions inside of the North Pacific Gyre, where trash is being piled up at either side by the water that's being piled into the center, and it has nowhere to go. It doesn't easily get out of this gyre because you have the current moving around it, and it doesn't easily sink either, and you wouldn't want it to sink either way. But you have garbage piling up in these two spots. And the Great Pacific Garbage Patch is an unintended consequence of Ekman transport, basically. A less deleterious one, unless you're just irritated at how cold Antarctica is the Antarctic Circumpolar Current. It is essentially a large gyre where two separate winds are causing perpetual circular motion around the Antarctic continent. You have westerly winds from the South Pacific and from the South Indian Ocean getting deflected by the Coriolis effect on either side of Antarctica. The water flows from the west towards the east and perpetually flows around Antarctica as a result of this, because there's no continents blocking it. And because there's no continents blocking it, it can gain speed and go quite fast. Remember that it goes quite faster than any of the other surface currents in the world. And this ends up sort of trapping whatever is inside of it, the same way that the Great Pacific Garbage Patch kind of traps garbage inside of it. Something I want to emphasize here is that you'll notice how the winds kind of look like they're approaching the continent but don't quite reach it. And lines that look like they're doing that is another consequence of the Coriolis effect. The direction you have something, these winds are being channeled further and further towards the South Pole, but they never quite reach it because the Coriolis effect will cause them to be deflected before they reach it. You would not get this current forming if Earth was not spinning. Because Earth is spinning, that causes the water to rotate around the continent. And this current blocks any potential warm currents from reaching Antarctica. Remember that water can store a lot of heat. You can pump a lot of energy into water without it heating up noticeably or boiling. It takes a lot of energy to boil water. So what can happen is that in a case like the Gulf Stream, which you can see on this diagram close to the coast of North America, is that relatively warm water from the equator can travel quite a ways before losing much of its heat, and the water itself is not going to be that much noticeably warmer, but when it releases its heat, that can have quite a big difference on the surrounding air and land, and will contribute to the surrounding area being relatively mild. So hypothetically, a warm current like that could approach Antarctica, and when the water released its heat close to the coast, it could warm up the land and the air. But that doesn't really happen. Currents do not easily cross the Antarctic Circumpolar Current. And for one reason, for one thing that has to do with it being so fast and so strong and so consistent, that other slower currents simply aren't going to get across without being absorbed. But there's the other fact that water, even though we think of it as being one gigantic ocean, different moving masses of water in the ocean are going to have different temperatures and different levels of saltiness or salinity, and that's going to affect how dense they are, and that's going to affect how easily they mix with other layers. We talked about the Antarctic Convergence before, and the Antarctic Convergence is an example of a front where you have two distinct water masses being brought by currents, and they don't mix very well. You would expect there to be a smooth gradient of mixing between colder and warmer water, but in fact, there are relatively narrow zones of relatively rapid mixing, and that's why the Antarctic Convergence, if one crosses it, goes from the north to the south. That's why one feels it as a pretty strong temperature drop, because the relatively little mixing is ineffective and happens in a pretty small zone. You get a pretty, you pass from one zone, go through the front, and then pass to the other zone, and you've actually rapidly dropped temperature. This is why this is a large reason why the Antarctic Convergence is often used to define Antarctica, because it separates literally the waters surrounding Antarctica from the waters of the other oceans, and to a big extent defines what is the Southern Ocean. The Antarctic Circle is often, the Antarctic Circle, remember, has nothing to do with ocean currents. It has to do with light. And recall that not all of Antarctica actually lies south of the Antarctic Circle, but all of Antarctica does lie south of the Antarctic Convergence, the polar front as it is labeled here. And that polar front is where the coldest water from Antarctica is mixing very ineffectively and poorly with the water from the other oceans. And you get quite a temperature drop across that front. In the next part of the lecture, I will continue talking about ocean circulation with talking about deep water circulation, and then move into modern climate research and a brief discussion of how the Antarctic climate actually got here, and what implication and what got us here from Antarctica's past worlds, which is something I'll elaborate more on in next week's lectures. All right, that's the end of half one.